Hi, let's talk about bucket sort. Let's understand these two problems to get an idea of bucket sort. In the first situation, we have numbers in range from 1 to 10 raised to the power 8, and these numbers are uniformly distributed in this range. In the second situation, we have floating point numbers, and these numbers are again uniformly distributed in range from 0.0 to 1.0. So 0.0 is included and 1.0 is excluded. So all the numbers are greater than or equal to 0.0 and smaller than 1.0. Now let us clarify what do we mean by uniform distribution. If you have 100 numbers, for example, then these 100 numbers will be like this. Around 10 numbers will be in range from 0.0 to 0.1, 0.1 being excluded. Around 10 numbers will be in the next slot from 0.1 to 0.2, 0.2 being excluded. So if you have 10 slots, then around 10 numbers will be there in every slot. And if you have 5 slots, if you have distributed your whole range in the 5 slots, then around 20 numbers will be there in every slot. To give you more idea, for example, if you have 1000 numbers to be sorted and you have this range, and if the numbers are uniformly distributed, and if you have divided this range into 10 equal sized parts, then every range is going to have 100 elements around. And if you have divided the range into 5 equal parts, then every range is going to have around 200 elements. So this is what uniform distribution is. A simple solution to sort these numbers is to use any n log n comparison based sorting algorithm like merge sort, heap sort. And with these sorting algorithms, we can get the time complexity as n log n. But we are not using the fact that numbers are uniformly distributed in a given range. We could think of counting sort. We could try applying the counting sort, but counting sort would not work in this example particularly because we can't use elements as indexes because elements are floating point numbers. In this situation also, if you try using counting sort, then you would need a lot of extra space. Suppose you have only 100 numbers to be sorted, then you would need extra space for a range of 10 raised to the power 8. So which is too much. So counting sort would also not be a good fit. Bucket sort is a sorting algorithm that works in linear time when your data is uniformly distributed across a range. Now please pause this video and think of a sorting algorithm that will use the uniform distribution fact and will sort the data in linear time. In case you are aware of hashing with chaining, this is going to be similar to that. If you're not aware, no problem. We are going to talk about detailed algorithm now. Let us now get an idea of bucket sort. With this example, we have these 9 elements which are uniformly distributed across the range from 0 to 99. So in bucket sort, we first divide the range into multiple buckets. So we have a range of 100 elements from 0 to 99. Here in this example, I have created 5 buckets. Now, why are we creating 5 buckets? Why not 10 buckets? Why not less buckets? We'll talk about that. It's actually all about time versus space trade-off. So I've just taken a number 5 and divided this range into 5 ranges. First range contains the elements from 0 to 19. The second range contains the elements from 20 to 39. The third range from 40 to 59. Fourth range 60 to 79. And fifth range 80 to 99. Once we have created these buckets, what we do is we traverse through the input elements, and for every element we decide in which bucket this element should be going, and we put that element in that particular bucket. So 20 went into this bucket because this is 20 to 39. 88 went into this bucket. 70 went into this bucket. 85 here, 75 here, 95 here, and 18 into this bucket, and so on. So once we have moved all the elements into appropriate buckets, the next step that we do is we sort individual buckets. So this bucket has only one element, no change here, no change here. This is empty bucket, so no change here. This bucket has 3 elements and this was the original order. We sorted them and got this. Now this bucket has 4 elements. we sorted this bucket and got this, right? Once we have sorted individual buckets, our last step is to join these buckets. So we first put elements of the first bucket, which is 18, then second bucket 20, third bucket is empty, fourth bucket has elements 60, 70, 75. We put these 3 elements. Now last bucket has 4 elements, so we put the last bucket elements. And you can notice that all the elements of array are sorted now. Now the question arises, how do we sort individual buckets? We can use any standard sorting algorithm to sort the individual buckets. If we are sure that individual buckets are going to have less number of elements, then we can use insertion sort. Insertion sort is the best suitable algorithm for small amount of data. Let us now analyze bucket sort in more detail. The question arises, how many elements are going to be there in individual buckets? See, if we have total n elements in our input array, and if we have k buckets, and if we are assuming that our data is uniformly distributed, then how many elements we will have in individual buckets? We will have n by k elements on average, if the data is uniformly distributed. If every element is equally likely to go in any of the buckets. So if we have k close to n, for example, if k is equal to n, then we will have approximately 1 element in every bucket, which means we are going to take constant number of time to sort the individual buckets. Even if k is half of the n or 1/3 of the n, in those cases, you are going to have 2 elements on average in individual buckets or 3 elements in individual buckets, which are again constants. And even if you have slight variation from uniform distribution, say you have 5 elements or 6 elements in individual buckets, even then you are going to take the constant time to sort the individual buckets. And the final step is to simply join these individual buckets. So joining is going to take linear time. So we took linear time to distribute these elements into individual buckets. Then we took linear time to sort all the buckets, assuming that sorting individual buckets take constant amount of time because we have uniform distribution and we have number of buckets proportional to input number of elements. So overall, we are going to take the linear time to sort the individual buckets under these assumptions, uniform distribution and number of buckets are almost equivalent to n or half of the n or 1/3 of the n. And once you have sorted, joining them will again take linear amount of time. So we are taking total linear time to sort the elements if we have n of buckets and we have the data uniformly distributed. Please note that this algorithm might work really bad if your data is not uniformly distributed. For example, if all the elements, they go into the same bucket, what will happen? If you are using insertion sort to sort the individual buckets, assuming that you are going to have uniform distribution and less number of elements in every bucket. But if this does not happen, then you are going to take big O of n square time to sort one bucket, and which is a worst case situation for the bucket sort. Let us now talk about implementation details of bucket sort. What we actually need to implement as a bucket sort program. So for simplification, we are assuming that we are given number of buckets as input, so that we don't need to decide how many buckets to use in this program. So we are given an array and we are given number of buckets. In this example, number of buckets is 5 and number of elements of the array are these. Now, how do we find the range of the elements? We can find the maximum element in this array, that is going to be the upper limit, and lower limit we can assume as 0. So in this example, our maximum value is 99 and minimum value we are assuming as 0. So we have total range from 0 to 99 and we need to divide this range into 5 buckets. So we'll divide this way. All the elements that are from 0 to 19, they will go into the first bucket, 20 to 39, second bucket, and so on. And that is how we'll put these elements into the individual buckets. Let us now see this example. Here we need to divide the range into 4 buckets and our range is from 0 to 80. So this range has 81 elements in total. And this becomes slightly challenging program to implement yourself. so that you divide these 81 elements into 4 buckets. So one of your buckets is going to have an extra element in the range. And once you have decided the ranges for the 4 buckets, then you need to put these elements into individual buckets. So this is all you need to implement. You need to decide the ranges for individual buckets. Then you need to put these elements into individual buckets. Then you need to sort the individual buckets, and then you need to concatenate them. Now please pause this video and write a function that takes an array as an argument, number of buckets as another argument, and then sorts the array using bucket sort. Let us now see the implementation. This side we have Java implementation, and here we have C++ implementation. So in these implementations, we take an array as an argument. We also take number of buckets as another argument. And inside these implementations, we are first finding the maximum value in the array. Once we find the maximum value, we are creating k buckets. In C++ implementation, we are using an array of vectors, right? The size of this array is k, and we call this array as bkt. In Java implementation, we are using an array list of array list. And once we have created k buckets, we traverse through every input array element. For every element, we decide in which bucket this element should go, and we put this element into that particular bucket. We'll discuss this process in detail. This has been demonstrated here step by step. We'll talk about these steps. Once we have added elements to individual buckets, we sort the individual buckets. So this is where we sort in C++ code, and this is where we sort in Java code. After sorting individual buckets, we concatenate all the buckets. And concatenation or joining of all the buckets is really simple. We simply traverse through all the buckets, and if a bucket has elements, we traverse through all the sorted elements one by one and put these sorted elements at the next index. So we have used an index variable, we initialize it as 0, traverse through all the buckets, traverse through all the elements of the current bucket, and put the elements at the next index. That's the simple concatenation task. Let us now see how do we decide bucket index for every element. Let us see this example array. In this array, our maximum element is 80, but we initialize the max value as 81. I'll shortly discuss what is the reason for incrementing it by 1. After we have initialized our max value as 80 plus 1, we traverse through all the elements, and for every element, we use this formula to decide the bucket index. So when I is 0, we are going to get the bucket index as 4 into element at 0 index 30 divided by max value. So we are going to get 4 into 30 divided by 81, which is 120 divided by 81, and we are going to get the index as 1. So we put 30 at index 1. Now we come to the next element 40, and we get the index again as 4 into 40 divided by 81, 1. Then we go to the next element, we get the index as 0. Then we go to the next element, which is our maximum element, and we get the index as 3. And suppose we did not do max value plus plus, what would have happened in that case? We would have got 4 into 81 divided by 81. We would have got the index as 4. And we have valid indexes from 0 to 3. That's the reason we increment max value by 1, because there exist max values in the array, and for these max values, we are going to get a new slot. So if your range of elements is from 0 to x, then we divide by x plus 1. We choose the maximum value as x plus 1 to get the appropriate indexes. In this particular example, if we apply this formula for any element in range from 0 to 80, this is how these elements are going to be divided. For elements from 0 to 20, we are going to get the index 0. For elements from 21 to 40, we are going to get the index as 1. For these elements, we are going to get the index as 2. For these elements, we are going to get the index as 3. So every element goes into one of these 4 indexes. And why is this happening? Because we have taken this as 81. If we do not increment it by 1, then for 80, we are going to get the index as 4, which is out of bound. After we have put all the elements into individual buckets, we sort these individual buckets, right? We are going to sort these individual buckets using sort function in C++ and collections.sort in Java. So after sorting individual buckets, you will get the first bucket as 5, 10, 12, second bucket as it is 30, 40, and third bucket after sorting will become 70, 80. And once we have sorted individual buckets, we are going to concatenate them, right? So we begin with index equal to 0 and we traverse through all the buckets. Then we traverse through all the elements of current bucket. So we put 5 at index 0 and then we increment the index. Then we put 10 at the next index and we put 12 at the next index. Then we traverse through this bucket and put elements of it. Then we see next bucket is empty. So we traverse through the final bucket and put elements of this bucket into the array. So this is how our array becomes sorted using bucket sort. Let us now talk about time complexity of the bucket sort. In this time complexity analysis, I am assuming that number of buckets are approximately equal to number of items in the input array. In the best case, we'll have perfectly uniformly distributed data. And when you have perfectly uniformly distributed data, and if you have n buckets, then every item is going to be in a different bucket. So sorting individual buckets is going to be big O of one time or constant time, because there are one elements in individual buckets. Even if there are slight variations, that's constant. And then we are concatenating all the buckets, which is big O of n operation again. So our overall time complexity is going to be big O of n. Even if you use insertion sort to sort the individual buckets. Why do we use insertion sort? Because insertion sort is the best algorithm when you have small number of elements to be sorted. Now in the worst case, what will happen is your data is not uniformly distributed and everything goes into a single bucket. And if you use insertion sort here as well, then you are going to have big O of n square time in the worst case. But if you use an n log n algorithm to sort the individual buckets, then your worst case can also become big O of n log n. But please note that if you're using n log n algorithm to sort the buckets, then it won't be a good idea if your data is uniformly distributed. So bucket sort is the best suitable algorithm when your data is uniformly distributed across the range.